Okay, the last thing I want to discuss in this chapter is actually probably one of the most important concepts. Newton's equations seems to be good for system of particle. For a single particle. That's how it was described. But in reality, we have bigger systems that have dimensions. They might have many internal components, like a car. How do we deal with those situations? And as it turns out, it is actually quite straightforward and quite useful to know why we can use Newton's equations for bigger systems without any issue. To see why it's happening, consider a system of particles. A bunch of particles, they do not necessarily need to have any relation with each other. It doesn't have to be a rigid body, just a bunch of particles floating in space. And we call the collection of all these particles a system. So the setting is as follows. Let's assume each of these particles is subject to some net external force. So each particle has some external force. This is F1, F2, and so on. Also, from every single particle, there are internal forces that, I don't know, let's call F, whatever. There are a bunch of internal forces from each of these other particles on the particle of interest. So all these F's, little f's, are internal forces between particles. So now I know for each particle I have a bunch of internal, a bunch of external. I can write for any particle I can write the equation of motion. Sum of forces equals mass times acceleration. And these are for each particle, like particle I. And I can write it as the net force acting on particle I, like F1, plus sum of all internal forces acting on that particle equals mass times acceleration of that particle. Let's call it mass I, mass of particle I. And I can write essentially copies of the same thing for all other particles, for particle 1, particle 2, and so on. So I have a total of, I don't know, big N number of equations. And what I can do is add all equations together. So all the right-hand sides, I add them up together, or all the left-hand sides, I add them up together. What I end up with is an equation that's sum of all external forces acting on a particle plus sum of all internal forces that all particles act on all of each other's equals, let me write it better, sum of all mi times ai. Oh, by the way, all of these vector. So this is the summation of all equations of motion. But I want to bring your attention to one thing, that when we are talking about internal forces, like this one, let's draw it with a different color. This is F of 3 on 1, and according to Newton's third law, there is going to be some F1 on 3, exactly the same magnitude but opposite direction. And it is the case for all internal forces. For any force, there is another one opposite and equal to each other. So when I add these two together, they add up to 0. And that happens for all internal forces, which means, let me clean up, I don't want to keep this, which means this term is 0. So summation of all internal forces add up to 0. And what I end up with, sum of all external forces equals sum of all mi times ai. That is already a very good expression. It means when I'm talking about a system of particles, I can actually very safely just ignore all internal interaction between particles and only focus on external forces, sum of all external forces, and they are related to the acceleration of the system. But maybe that is not quite as useful. So let's take one more step. When you have a system of particles, this is a reminder. You have a system of particles with a bunch of position vectors, or position of each particle. You can define, this is defined, position of center of mass, let's call it R bar, to be essentially the average of all positions weighted according to the weight of each particle. So all the mi or I divided by total mass, that is the center of mass. Oh, I didn't write it down. Center of mass. It is going to be somewhere around the center. This is R bar, or actually, no, let's call it RG for center of mass. I don't know why G. But anyways, let's call it RG. Essentially where the average mass of the particle is concentrated. When you have that, you can actually take multiple derivatives of this and you end up with R double dot G acceleration. Because all the masses are constant, let's assume they are constant. Mi R double dot I divided by total mass mi. And now let's see what happens. This one, this thing is the same as what we calculated before, equals mi ai mi. So I can rewrite this and write acceleration of center of mass, acceleration of that point, times the total mass. Well, let me write it this way. Let me do this. So this thing is total mass, and this one, let's make it simpler, m, total mass of the system. A mass times acceleration of center of gravity is mi ai, and this is what we had before. So in the end, sum of all forces, external forces, equals mass times acceleration of center of gravity. So this is a very, very useful way of thinking about system of particles, because first of all, it can tell us ignore about all the internal forces. The only thing that matters are the net external force. And also, you can forget about all individual particles. Just look at the total mass of the system and pretend the entire mass is concentrated at a point called center of mass, and look at the acceleration of that virtual point. So if you know the center of mass, you know where the center of mass of a system is, you can find the acceleration of that point and relate that to all external forces. So pretty handy when you're dealing with systems that are not just a single particle, which doesn't actually exist. A car, a satellite, a robotic arm, all of these, you can find the center of gravity and start calculating forces that cause the motion of that point. Okay, that is, I think, all I wanted to say. Yeah, I think that is all. So in class, we look at a lot more examples, and we should be good for this chapter. So I'll end this here. See you later.